Hello, in this video we will define an important concept called the interplanar spacing of a given set of lattice planes, and we will derive this for the cubic system. So, this interplanar spacing has a universal symbol DHKL, we will use that. It is an interplanar spacing between successive HKL planes. So, if you have parallel planes passing through the corners of the unit cell, spacing successive planes passing through the corners of the unit cell. Another way of looking at it is the same distance will also be equal to distance between origin and the nearest HKL plane. So, once we see some example, it will become clear. So, let us first look at DHKL. You can derive formula for DHKL, and in the books you will find for various crystal systems, but the geometry becomes very complicated for crystals which are not having axes which are orthogonal. So, we will derive this for the simple case where the axes are orthogonal. So, we are assuming the crystal to have orthogonal axes, and that is a crystal system in which all the three interaxial angles are 90 degree. You know that such systems there are 3 out of 7, the cubic, tetragonal and orthorhombic. For these systems it becomes simple, the derivation becomes simple. So, we will do that. So, let us say that this is the origin and these are the 3 axes of my orthogonal system, could be cubic, could be tetragonal and could be orthorhombic. So, to keep it general, let us start with orthorhombic, later on we will specialize for tetragonal and cubic. So, all of them have alpha, beta, gamma 90 degree. Orthorhombic, the 3 lattice parameters are not equal, A not equal B not equal C. Tetragonal, A equals B and not equal C, and in cubic all are equal. So, this is the only difference. So, let us start with the general case of orthorhombic system. So, we have 3 orthogonal axes, and let us say that the first HKL plane away from the origin is this. It intersects the x axis at A, y axis at B and the z axis at C. So, ABC is my HKL plane, and again like in the last exercise for finding the plane normal we had done, we drop a perpendicular ON onto the plane. So, ON is perpendicular to ABC. which has Miller indices HKL. Now, let me connect N and A and let me look at this triangle O N A. So, remember first that O N is the distance from the origin to the HKL plane, and that is why by the definition which we gave, O N is equal to DHKL. Now, let us look at this triangle O N A. So, I am redrawing this triangle O N and then A. Note that O N is the foot of the perpendicular from O to the plane. So, O N is perpendicular to the plane ABC. So, O N and N A is a line lying in the plane. So, O N and N A are perpendicular. So, I have a right triangle O N A. O A, you now know, can be written, the magnitude of O A can be written as A by H, that is the intercept, the reciprocal intercept. HKL is the plane. So, the first number is the reciprocal of the intercept. So, that is 1 by H, but this intercept is in terms of the corresponding lattice parameter. So, we have A by H. So, O A is A by H. O N by our definition is DHKL. Let me call this. So, OA was also the direction of my x axis. Let me call this angle theta 1. So, the first direction cosine of O N is the cos of the angle O N makes with the x axis. So, this is cos theta 1, which is nothing but the base is DHKL by the hypotenuse, which is A by H. So, DHKL by A by H, which we can write as H by A DHKL. Similarly, the second, you can form a similar triangle, let us say with B, and think of the triangle ONB. Let me do that. Now, I have O, I have N, and let us say here is the B, this direction is the y axis, this is theta 2, O N is still DHKL, and N O B which is the hypotenuse is the second intercept of the plane. So, this is B by K. The reciprocal is of K is 1 by K and multiplied by the corresponding lattice parameter, which now, since we are talking of orthorhombic, is different from A, it is equal to B. So, O B becomes B by K. So, our second direction cosine of ON cos theta 2 becomes DHKL, this time B by K. So, I have K by B DHKL. Now, we have seen the pattern. So, I can write the third direction cosine simply by looking at the pattern. Cos theta 3 the lattice parameter now is C, the Miller indices is L. So, I divide it by C by L. So, I get L by C DHKL. So, if we now the direction cosines have the property that sum of the squares of the direction cosines cos square theta 1 plus cos square theta 2 plus cos square theta 3 is equal to 1. This is the property of direction cosines. So, we use this property. We have already seen that cos theta 1 was h by a DHKL. So, I square it, cos theta 2 was k by b DHKL. So, I get k by b square DHKL square, and I get L by c square DHKL square. So, you can quickly see from here that now we have derived the formula. I can take DHKL common and take it on the other side. So, 1 by DHKL square is nothing but h square by a square k square by b square L square by c square. This is for orthorhombic. We can quickly derive the formula, the special cases for, so for orthorhombic, we just derived that 1 by d HKL square is h square by a square by b square L square by c square. For tetragonal, all you have to now result for tetragonal you can get simply by substituting for b equal to a. So, you have h square by a square c square, or you can write it h square plus k square by a square c square. And for cubic, all the 3 parameters will be equal. So, for cubic you get even simpler formula. If you equate all of them, or this sometimes is simplified for writing directly in terms of DHKL. So, DHKL we rearrange and take the square root, T square K square and this is for cubic. So, we will use these DHKL spacing particularly in the topic which we are now going to move, that is the topic of X-ray diffraction. So, there this the concept of DHKL, the interplanar spacing between planes, will form an important role.